Okay, and on this example, we are going to investigate the transform function of a quadratic function. So we are about to assess or investigate the transform function of a quadratic function. And the transform function form of a quadratic function is given by y minus k is equal to a x minus h square, which is also equivalent to y is equal to a x minus h square plus k, giving us the vertex h k, and the vertex is the point where the parabolic curve is cut into two or divides into two. So it's in technical terms, this is the maximum or the minimum point of any parabolic graph. At the same time, it is also the point of symmetry, because it divides the parabola into two half parabolas symmetrically. So it's also the point of symmetry. So let us investigate this given function here. Y is equal to 3 minus 2 times x minus 1 by way of assessing the transform function or the vertex form function. So in the vertex form function, all we have to do is, let us move this O1 a little bit here. And we don't really need this underline here. Okay. So first, we have to assess the vertex of our parabolic function or our quadratic function. So in this case, first we are going to assess it through a table. So let's have a table for x and y, as we always do. Okay, let us set our tables of x and y values. And in this case, I'm going to begin by graphing or plotting the vertex. Our vertex here, in this form, 3 minus, this is y is equal to 3 minus 2x minus 1 square, and my vertex is equal to 1, because our h is 1 and our k is 3. So we have 1, 3. So starting from our vertex, I would get the points from the left and from the right, because the definition of our vertex is that it is a point of symmetry, meaning that it is the point at which all the points on its left and on its right are balanced. So whatever you choose as long as you choose the same scales for the left and the right, then you would get a half parabola that are symmetrical. So let's do that. So since my vertex is 1 and 3, of course I would define my values for x and my values for y by getting the values of x, and I would set my x and y axis. So this is my x-axis and this is my y-axis. Okay, so because I want to examine what the yield for x values to the left and to the right of the vertex is, then I would put my vertex on the center. So it's like the center of attraction. We have the vertex here at 1, 3, and then I would choose 0 and negative 1 on the left and 2 and 3 on the right of the vertex. So let us take the grids out for a while. If my x is negative 1 in this this equation. So we put our x equals -1 on this equation. So we will have 3 minus 2 times -2 square. So -2 squared is just 4. And 4 times -2 would be equal to -8 plus 3. So we would have -5. Am I correct? So we have -5. If my x is 0, then I would have 3 minus 2 times 0 minus 1. So that's just 3 minus 2. So we have 1. And if I have 2, then that's 3 minus 2 minus 1. So 3 minus 2 only. So that's 1. And if I have 3, so 3 minus 2 times 2 squared. So 4, so 8, so it's -5. So as you could see, guys, okay, we have a symmetrical value. So these are symmetrical values from the right of your vertex, or your vertex is here, and from your left, from the left of your vertex. So let us try to, or let us graph the points I've taken. So first, I have to place this on a balanced grid line, okay, just to be sure that I would get the accurate values. So what is happening here? Okay, I just want my y to be moved. That's it. So what's happening? Okay. Let's move the x here. Okay. Now we have, but wait, this is not balanced. So we have to move this a little bit like upwards. So now it's good. So we have -1 and -5. Where is -1 and -1? Or -1 and -5? -1 and -5 is somewhere here. So this is -1. This is -1, 2, 3, 4, 5. So I'm missing one grid line. So okay, just extend it. Where is 0, 1? 0, 1 is 0 and 1, so it's here. Where is 1, 3? So 1, 3 is, let's make it another color because it's our vertex. Okay. 1 and 3. I'm sorry, it's here. 1 and 3. Okay. 1 and 3, 2 and 1. So 2 and 1. And finally we have 3 and -5. So it's here. Okay. Now let us see, we connect the graph. We're going to make use of this color to demonstrate the graph. Okay, so we have this graph and this graph. So it should be a smooth curve, but this is the best that we can do with a pen. So let us now examine the point of symmetry. So this is your point of symmetry, this point here. Okay. Now we take this out. We want to take out the grid so you could see clearly what is happening to the graph of our function 3 minus 2 times x minus 1 squared. So you can see the vertex upwards or on the maximum. So this is a maximum. Okay, this is a maximum. Okay, I want the indigo. So this is a maximum. We have a vertex of 1, 3. Okay, and we have a specific points here. First point, second point, third point, and fourth point. And you can see that we have a symmetry at x is equal to 1. So at x is equal to 1, the graph on the right and the left are balanced. So they are symmetrical. They are half parabola across the symmetry. Okay, so let us have the concavity. So this graph has a concavity which is downwards. Okay, so it is concave downwards or opens downwards. What else? At this point, let's say this is portion A and portion B. So at portion A, what do you notice at portion A? It is positive and decreasing, so positive and decreasing. And at point B, it is negative and also decreasing. Okay? And in general, okay, let us have a generalization here. So in general, when you have a transform form of the quadratic function, if our A is equal to 0, or I'm sorry, if it's greater than 0, then your concavity would open upwards. So your concavity is upwards. And if A is less than 0, then your concavity is downwards. You have a minimum here because the vertex is at the lowest point, and you have a maximum here because the vertex is at the maximum points. Okay, so that is the generalization for involving A of quadratic functions, and especially when we are dealing with the transformations of quadratic functions. So I hope you are cleared up on your questions about the quadratic function in detail. So thank you for watching.